Yeah, page 15. And thanks to somebody, not me, we have shiny new attendance sheets. So sign in there. All right, so if we just glance superficially at page 15, we're talking about the eye. Not much functionality, just anatomy, just so you can go into the lab and dissect the eye. And again, looking superficially, you've got letter A, letter B. So the eye is divided into chambers and layers. So we'll talk about the three chambers and we'll talk about the three layers. Actually, we'll deal with the layers first and then the chambers. So I'd give myself a clean sheet of paper, turn sideways, match it up to the board. We'll have a picture here and then other stuff over there. It's kind of, I don't know, odd, weird, whatever word we want to use, but when you study the eye in pictures, whether you draw it or whether you're looking in your textbook or your lab manual, you tend to use sagittal pictures, but it's easier to see the parts of the eye with coronal pictures. So if you've looked in the atlas or the lab manual at the actual photographs of the cow eye, which is what you'll be dissecting, you've seen that those are coronal pictures. That's the way you'll cut the eye in the lab, okay? Coronally, a front piece and a back piece. Yet when we study it in pictures, we tend to do it sagittally. So starting with the first layer, you can see that it consists of the sclera and the cornea. The first layer is called the outer or supporting layer. And the posterior part of this outer or supporting layer is the sclera. That's the white of your eye. So if you just look in the mirror or look at the person sitting beside you. In the anterior part is the cornea. Which is clear. Now they're continuous with each other. A circle, of course I can't draw a circle, you probably can, but they're continuous with each other, as you can see. But the difference is the posterior part, the sclera is white, the anterior part, the cornea is clear. They're thick, they're tough, supporting layer. Think about a tennis ball. The skin, maybe it has another name, but the skin of the tennis ball, or the shell of the tennis ball. That's the supporting layer. The tennis ball is filled with air. The eye is filled with fluid. If you puncture the eye, you lose the fluid. And there are actually two different types of fluid, and we will get to that. So functionally, this is all about structural integrity. Right, the middle layer is also called a vascular layer. You'll see both of those words on your lecture notes. The posterior part of the middle layer is called a choroid. The S should not be there. The choroid works like a mirror. reflects light. Let me show you exactly what I mean. Don't draw this on your paper, because I'm going to draw it and then I'm going to erase it. But as light shines into our eye, it bounces off of the choroid, just like if you shine a flashlight at a mirror. So again, the choroid works like a mirror. It's a reflective surface. The reason that the light bounces off of the choroid is because the receptors, the light-sensitive cells, are not sitting here like this to catch the incoming light. The light-sensitive cells are sitting here like this, so the incoming light has to bounce off the choroid. That means that left and right are backwards. Many of you remember one of the old 35mm slide projectors, or even the overhead projectors that occasionally you'll still see in a classroom. If you take the slide or the transparency and you position it the way you want it, what seems normal, and then you get it projected on the wall and everything is backwards. We'll get into more of how backwards things are. But as it turns out, if you've ever been in the car with one of those people and they say, take a right here, take a right, they're correct. That is right. This is left. Or is it? Or am I even here? All right, so the choroid. As we move further anterior, we've got these things called ciliary bodies. The ciliary bodies produce the fluid that's in the eye. They also contain some little muscles called ciliary muscles. Now the ciliary muscles are microscopic. You're not going to see them. And so if you look carefully at your notes, big letter B, item 2, small letter b, ciliary bodies, ciliary muscles are in parentheses. You might want to asterisk that or something. It's one of those, okay, I'll know they're there, I'll know what they do, but I'm not going to be able to say, oh, there they are. Okay, so there are a number of things like that, and I guess I often use the word application or conceptual. Nobody in the room thinks they're going to be taking a practical, whether I administer it or it's in Florida, and you walk up to the pan, name the indicated structure, and you say, I'll be darned, he's got that pin right in a nephron. Looky there, he's pinned an alveolus. Okay, you know, they're microscopic things, and so there are a lot of things like that that come up. In other words, the nephrons are the functional units of the kidneys, the alveoli, the functional units of the lungs. Well, within the ciliary bodies, which you will see, are some little muscles called ciliary muscles, and we'll see what they do in a minute or so. That's the iris. The iris is the part of your eye that's colored. So you have blue eyes perhaps, or brown eyes, or green eyes. It's the color of the iris. The hole in the iris is the pupil. So the musculature of the iris is able to contract and relax, which allows the pupil to dilate and constrict according to the light levels. Let's see who's looked at their cranial nerves. Which cranial nerve innervates the iris, causing the pupil to dilate and constrict? 3. And what's its name? Well, you're right. Number 3, and you're right too. It's the oculomotor nerve. There's one more question in that arena. What's the name of this process of the pupil dilating and constricting? Huh?
Dilation.
Adaptation. Adaptation. So it's cranial nerve number 3, the oculomotor nerve, that innervates the iris, causing the pupil to adapt to changing light levels. So the process is known as adaptation, which consists of dilation and constriction. Then finally, we could add to that, if you go back to introductory material, what's the ANS? Autonomic nervous system, subcategories, sympathetic and parasympathetic. The sympathetic, I told some of you last semester, so I realize you weren't all privy to that, but I told you guys, if it sounds like something that goes with exercise, it's a function of the sympathetic division, so like increasing your heart rate, increasing the rate at which you breathe would be sympathetic. If it sounds like relaxation or resting, it goes with parasympathetic, so slowing the heart down, slowing down the rate at which you breathe. So with that in mind, which one of these would you say goes with dilation of the pupil? If you think along the lines of, when I dilate, I let more light in, I can see better. Sympathetic. Because if you're exercising, you might not want to, run into the wall, or
if you're in fight or flight, you want to get your eyes bigger.
If you're fight or flight, you want to, well, yeah, okay. So sympathetic goes with exercise and goes with dilation. Parasympathetic goes with rest and goes with constriction. Now I give you 2 drugs, methamphetamine or cocaine and heroin. Which of those would have the same effects as the sympathetic division, the methamphetamine or the heroin? Methamphetamine. Methamphetamine is going to raise your heart rate, isn't it? Does your raising heart rate go with exercise or rest?
Exercise.
Does your rising heart rate go with meth or heroin? So what's heroin going to do? Now I switched. We just talked about methamphetamine. What's heroin going to do to your pupils? Constrict. The pupils of somebody on heroin will be as tiny as the point of a pin.
So heroin is a downer?
Heroin's a downer.
Okay.
Yeah. So what are the pupils of somebody on cocaine going to look like? Fully dilated. They're going to be so dilated that you don't have an iris. What color are your eyes? No, they used to be blue. Now they're just black, like your iris, or like your pupil is. So why do you think the police officer that pulls you over at 3:30 in the morning, not that it's illegal to be driving at 3:30 in the morning, but most people aren't, and shines the flashlight in your eye, what's the police officer expect your eyes to do? Change how? Light shining in your eyes. Your pupils should constrict. If they stay fully dilated, you just got popped for speed. Okay, methamphetamine. Well, this won't necessarily show the heroin side of things. This will show the speed side of things. All right, so interesting stuff to think about, interesting ways to apply what we're talking about.
So you're saying that when your pupils dilate, usually your eyesight should get better? Because I know that in the
Well, okay, let's say I'm looking down here under the thing where it's dark. The reason my pupils will dilate is to let more light in. If I could put some drops in them that kept them from dilating, and I look down here, I wouldn't see as well as right now when I look down here and they naturally dilate. So the dilation lets more light in.
doesn't necessarily mean clarity, like when the doctor...
Correct, it does not mean that. It does not mean. And now when the doctor dilates your eyes, that puts the drops in to dilate them, the doctor's doing that to get the best possible view of your retina. All right. That's the lens of your eye. And your lens is anchored to the ciliary bodies. By some structures called ciliary ligaments. I'm going to put an asterisk by the ciliary muscles. I've already mentioned that they're microscopic. I'm going to put an asterisk by the ciliary ligaments. You might see remnants of the ciliary ligaments, but generally speaking, you won't see them. They're too tiny. You guys know how you have to focus a microscope to see with it? Yeah, stupid question, right? Of course, binoculars, a telescope, you have to focus. Now, many binoculars today focus automatically. Almost all cameras today focus automatically, but you can still buy, a really nice camera that you have to physically focus. Well, what's going on is you're focusing on an object based on its distance from you. As you look down at your notes, and then you look up at the board, your lens is changing shape to focus on objects that are different distances. You have the extreme of, say, some sort of fine work that you might be doing versus looking out the window across town at the mountain. So you have to focus on objects that are close versus a medium distance versus far away. So to do that, the lens of the eye has to change shape. The way the lens changes shape takes us back to these muscles. These ciliary muscles contract and relax, changing the tension on these ligaments, which changes the shape of the lens. It's very similar to musculoskeletal functionality. Except in that arena, we'd call these things tendons, wouldn't we? Muscles contract and relax, changing the tension on the tendons and causing something to move. Well, that's exactly what's happening. But they call them ligaments, not tendons. You'll also see them called suspensory ligaments rather than ciliary ligaments. So again, the microscopic ciliary muscles that are in the ciliary bodies contract and relax, changing the tension on these ligaments, which changes the shape of the lens. Which cranial nerve innervates the ciliary muscles, causing the lens to change shape? It's easy. It's the same one. Number 3, the oculomotor. What's the name of this process or phenomena of the lens changing shape to focus on near versus far objects?
Adaptation.
Well, adaptation was the pupil. But it does start with an A. Accommodation. Accommodation. So the ciliary muscles contract, relax, change the tension on the ciliary ligaments, changing the shape of the lens so that you can focus on near and far objects. This is known as accommodation. As you get older, it becomes more difficult to change the shape of the lens. Your ability to accommodate diminishes. And so while you may not wear glasses now, there's a good chance that you will by the time you're 30 or 40 or 50 or 60 years old. Some people get through their entire life without ever needing a corrective lens, but the older you get, the greater the chance that you will. Okay. All right, the final so-called inner layer is it's the retina. You've heard of the retina. The technical term is the neuroretina. It's the retinal layer or the inner layer. The neuroretina is composed of photoreceptors. Receptors, like we've talked about so many times.
Just real quick, you said that accommodation was the ciliary ligaments contracting and like lengthening to change the shape of the lens.
Not exactly. So the ciliary muscles contract and relax, which changes the tension on the ciliary ligaments,
Okay.
which causes the lens to change shape.
And when the lens changes shape, that's what lets light in and out?
No, that's what focuses the light. The let light in and out would take us back to the iris.
Oh, okay.
So that the adaptation
Okay.
is how much light we let in. The accommodation, the lens, is focusing on something. Like if you had a pair of binoculars and for some reason you wanted to read these small letters over here, let's say I don't know if you can see them or not, but let's say you can. So you had a pair of binoculars, well then you would focus on something relatively close. But then if you wanted to go look out the window at Pikes Peak, you'd have to focus the binoculars to see something much further away. All right, so the neuroretina, it's photoreceptors, trillions of photoreceptors. Photoreceptors are light-sensitive cells. Okay, so again, think about the instances when we've talked about receptors and threshold. So I touch this. Receptors in my fingers are stimulated. Chemical gates for sodium open. And if enough sodium moves in through those chemical gates, the cells are depolarized to threshold, at which point the voltage regulated gates open and an action potential occurs. We've had receptors for acetylcholine on the downstream neuron. We've got two basic types of photoreceptors here. Rods, which give you black and white vision only, no color, and cones, which are what give you the color vision. The rods are more light sensitive, and the cones are less light sensitive. So since the rods are more light sensitive, they're more sensitive to light. Boy, that's helpful. The rods are more light sensitive. That means they're more sensitive to light. Well, that means it doesn't take as much light for the rods to reach threshold. It takes more light for the cones to reach threshold. Now just think about this. It'll become something that you absolutely do not have to memorize. If it's dark, can you see? Can you see the door and the doorknob and the coffee pot and whatever, I don't know where you live, but can you see? Of course you can see. But can you see vivid colors in the dark? No, you can't. The reason you can't see vivid colors in the dark is because you don't have enough light to depolarize the cones. You're depolarizing the rods, but you're not depolarizing the cones. Imagine a quilt, a homemade, handmade quilt on the wall. Your grandmother made it 100 years ago. And it's dark. You'll be able to see the shapes, the patterns, but you won't be able to see the vivid colors. Now, when I look up there on the back row, I really can't. Okay, your coat, shirt, whatever it is, has got to be red, orange, pink, something, versus everybody else's is more of a blue, black, gray thing. But I can't see distinct colors. And I don't know what you guys can see. I'm under a light, so you can probably see just fine. Anyway, I think that should be clear. Now the photoreceptors, are they here? Or are they here? What did I say earlier? Light comes in. So the photoreceptors are on the back side of the retina. So we need to put something in our picture to remind us. Remember, guys, the light comes in, bounces off the choroid, and strikes the retina. So we need something in our picture to make that point. We're not trying to draw a very anatomical picture. We're trying to draw a diagrammatic picture that helps us remember how things work. So you can do whatever you want, but what I'm going to do, what's going to work for me, is I'm going to put circles on the back side of the neuroretina. And these circles represent the receptors. Now look, wrap your brain around, stop whatever you're doing and pay attention, please. Not that you're not paying attention, but I don't want you to think that the retina is one thing and the photoreceptors are something else. No, the retina is the photoreceptors. The photoreceptors comprise the retina. This is just a diagram. So we're trying to show that the photoreceptors are on the back side of the neuroretina. Now they're light-sensitive cells. And of course, if we have a receptor, the structure leaving the receptor is an axon, just as if we have a basic neuron, the structure conducting the signal away from the cell body is the axon. So leaving each of these receptors is an axon, and all of these axons are not little streams in the eye that you're going to see. They're part of the neuroretina. You know what the neuroretina is going to look like when you get into the lab? A sheet of wet toilet paper. Little sheet of toilet paper the size of a quarter. And if it's nice and flat and smooth, you'll appreciate it. The chances are it's going to ball up and it's going to look like a piece of wet toilet paper that somebody's wadded up. The reason it gets like that in the dissection is because the eye is under pressure. And when you pierce the eye, to section it coronally, it implodes. Doesn't explode, it implodes. So each of these receptors has this axon, and yes, I'm tired of doing this.
Where are the cell bodies?
The little circles would be the cell bodies,
Okay.
as well as the dendrites. Because they're receptors, they don't necessarily have a body and dendrites. Okay, back to introductory material, back to those frickin' terms that never go away. We need a word that means group of nerve cell processes in the peripheral nervous system.
It's not
It's not
tracks.
tract, it's tract is group of nerve cell processes in the central nervous system. We need a word that means group of nerve cell processes in the peripheral nervous system. Nerve. You've all dissected the sheep brain at this point. You've seen the optic nerves versus the optic tracts. Where's the boundary? What's the dividing line between the PNS and the CNS when you're looking at the optic pathway? The what? The chiasma, exactly, the optic chiasma. Now, there are no, let's do this just to remind us that the light bounces off the choroid to strike the photoreceptors, which comprise the neural retina. Notice there are no photoreceptors right here. If you were to focus light right there, you wouldn't see anything. It has two names. The blind spot or the optic disc. That's pretty easy to see in the lab. In fact, guys, when you look at the neuroretina, not in all of the eyes, because a lot of the eyes, when you open them, it's going to implode and it's just going to look like wet toilet paper, nasty. But some of the ones where it stays nice and smooth, what you're going to see as you're looking at the neuroretina is all of these fibers, and they all converge to one point. Now you have to appreciate the fibers you're seeing are not really nerve cell processes. These nerve cell processes are microscopic, but because there's trillions and trillions of those fibers converging at that point, you will see something moving toward that central point. Okay, there's another structure on the neuroretina that we need to talk about. So I've mentioned blind spot. The one I haven't mentioned is the fovea centralis. The fovea centralis has the highest concentration of photoreceptors. You have the most photoreceptors per square area, whatever you could talk, for example, about square micrometer. So if we looked at two areas of the neuroretina, So my two squares represent two areas of the neuroretina. They're the same size, measured in square, whatever, millimeters, micrometers. The area on the right has many more photoreceptors in that square area. Well, you're going to get a sharper image if you focus on 100 photoreceptors versus only 10 or something. So the fovea centralis is the part of the neuroretina that gives you the sharpest image, the greatest visual acuity. Something that I think you will all be able to relate to. Is there a way to make this bigger? Nobody knows? Well, let's just pretend that you can read it. Perhaps you can.
Top.
So these are pictures. This is the file size. Okay, so that picture, it's a JPEG image, as you can see right here. You guys all have computers. I don't care whether they're Macs or PCs. They all use JPEG images. So that picture takes up 629 kilobytes. Now notice the name of that folder, Low Resolution Histology. What was the file size I showed you? 629. Now look at the file size of this one. Which is going to be the sharper image? Think about taking a picture and printing it. Think about taking a picture and using Photoshop or something and cropping and blowing up and printing because you're trying to get a pretty picture to go in a frame. So you could have a little 60 kilobyte picture that looks fine on a web page, but it's going to look like crap when you print it out and hang it on the wall. But you might have a 10 megabyte picture, which would be, of course, 10,000 kilobytes. You can crop it, blow it up, print it out, and it's going to look pretty on the wall. So these high-resolution images, that's your fovea centralis. I saw a hand somewhere.
It's like more megapixels in the camera.
It's like more megapixels in a camera. Yeah, it's another perfectly valid way to think about it. Yeah.
Does this play into, I mean, obviously this is the eyesight, but like when you're talking about having bad eyesight, does it have to do with multiple different things in the eye and just always depends?
Yeah, we'll
or-
talk about a few of those in a minute.
Okay.
So your brain automatically focuses things on the fovea because that gives you the sharpest image. The catch is it doesn't have any rods. So the fovea centralis doesn't do you any good at night. All right, let's draw some other pictures. Just got a little too full. this is just a sloppy abbreviated version of the picture we already have. So that I can label the chambers. So using the previous picture, what's this? Sclera? What's this? Huh? Cornea? What's this?
Lens.
What's this? What's the red thing? The purple.
Receptors.
Receptor.
Neuroretina is the name of the structure. What's this mess?
Ciliary.
Okay. All right, so, sounds like you're all with me. So we have 3 chambers at top of your notes. You'll see the chambers. So number 1 is the anterior chamber. Should be the very first one listed on your notes. It is. So what would you say if you were writing, no picture, the anterior chamber is the space between the blank and the blank.
Cornea and
Iris and the cornea. Exactly.